Then let's continue. But we all know that we study in complex variables theory about meromorphic function, holomorphic function, and all these strange functions. They have infinite number of poles usually. So if you have something like this equation can be satisfied in infinitely large number of locations on a complex plane. And you can argue yourself that that should be the case. Okay. What happens if the frequency is very high? If the frequency is very high, the number of guided modes becomes very, very large, right? If the frequency is very low, the number of guided modes becomes smaller and smaller. So when the frequency is very high, I can see the picture. That the picture is that lots of poles. Okay, very densely packed between the interval K3 and K2. When the frequency is very low, the number of guided poles can be 1 or 2 only. So what happened in between? What happened? Say if I go with high frequency case, if I start to lower the frequency, what happens to these poles? That's right, they migrate. Okay, these poles start to migrate. They start to march leftward. So we start with these poles. Okay? They start to migrate. If you lower the frequency, they migrate westward or left to the left. Okay? So they start with a large number here, but as you lower the frequency, they migrate. And then when they migrate beyond the branch point K3, what happens? The wave ceases to be evanescent in region 3 anymore. But the pole cannot disappear, right? This is a meromorphic function. The pole cannot disappear in thin air. You learn in complex variables theory, so they must appear somewhere else in the complex plane. Okay? So in region, if the wave is no more evanescent in region 3, it will be propagating, right? It will start to leak into region 3. Okay, start to leak into region 3. So in region, in this domain, the wave is experiencing total internal reflection at both boundaries. Okay? Over there, in my textbook, actually I have K1 and K3 reports. Okay? So what happens is that the mode starts to leak energy in region 3. They start to leak energy there. They still have total internal reflection in region 1, but not in region 3. What happens to this guided mode then? Guided mode leaks energy. Okay? It leaks energy, it must decay in the rho direction. So if I look at this K rho of this pole, it will have a real part and an imaginary part. The imaginary part must get bigger and bigger, because the imaginary part represents the decay of this wave in the rho direction. Okay? So as it starts to leak, it will start to acquire an imaginary part to K rho P. So it must migrate upward. This pole must migrate in this direction. Okay, and then a whole bunch of them line up all the way to infinity, migrating there like ants. Okay, you can imagine ants when they migrate, they go in the row. So these are marching ants going upward like that. So they acquire imaginary part. That part and that much you agree, right? It has to have an imaginary K rho part. So they must migrate outward. But I also draw it so that they're in the bottom Riemann sheet. Okay, they're in the bottom Riemann sheet. Why should they be in the bottom Riemann sheet? That means the imaginary K2z, or K3z in this case, is larger than 0. This must be a wave that grows exponentially in the z direction. Is this really a wave that grows exponentially? Well, if you look at this picture again, say if I put a source here, and then the wave starts to leak as it propagates and bounces around. And from a ray theory viewpoint, okay, this beam, this ray is stronger than this ray, is stronger than this ray, is stronger than this ray. Okay, so if I were to draw all these rays together, okay, and I'm going to see a weak ray. If I go further, I see a stronger ray, right? So the ray is actually exponentially growing in Z. That's why I draw them as such, that they actually are on the bottom Riemann sheet of K3. Okay? And those are called the leaky wave poles. They actually leak energy to region 3, and actually within this cone of observation, they actually grow exponentially in this direction because it decays exponentially in the rho direction. Because it decays exponentially in the rho direction, it must grow in that direction. Okay, and this kind of poles can be used to design what is called a leaky wave antenna. If you excite this pole, they actually can work for you instead of against you. They're not well-guided modes, okay? And of course, if this the reverse picture where in the textbook I put K1, 3, and K2, K3 are reversed, so in the textbook actually it starts to leak. If I put a source here, it starts to leak to the upper half space first before it leaks to the bottom. It's still evanescent here. And this is a picture I have in the textbook because I have the two reversed. The leaky wave antennas are useful. And how do you excite the leaky wave? In air, first of all, you have to have K rho less than K3 or K rho less than K1. That means that you have to have, say if I call this Kx direction instead of K rho, I want omega Kx to be larger than omega K naught. Okay, this is K naught. This is a condition for leaky wave. Okay, I guess. It's the other way around, right? No, Kx less than K naught, so it's this other way around. So this is the phase velocity. This is the phase velocity. So the phase velocity has to be larger than the phase velocity of air in order for the wave to leak. Okay, Kx has to be smaller than K naught, which is the case. All the Kx's are smaller than the K's of the region that they leak into. Okay? So one way to design a leaky wave antenna is to excite a wave with a high phase velocity or very slow phase variation. Okay, does that sound right? This is phase velocity, right? This is the formula for phase velocity, right? Omega over K. So I want to excite a wave that has very small kx, okay, and that can be obtained by, I think I talked about it in my course last time, CRLH structure. CRLH composite right left-handed structure, right and left-handed structure. You can get that by making transmission line structures that look like this. You can get a wave that propagates with a very small kx, with a very small kx in this structure. Okay, you can have omega kx. For this structure, the dispersion diagram can be like that. And you can actually get a mode to exist in this vicinity for this CRLH structure. And then if kx is less than, this is the cone, this is the light cone sort of. And if kx is less than these two numbers, or if this inequality is satisfied, this is a leaky zone. Okay, I think I went through this for those who took my course a few semesters ago. You can design this structure and have a dispersion diagram that looks something like this. Omega versus kx will look something like this. And then you can have kx very small for a certain range of omega. And this wave that propagates on this structure will start to leak. Okay, leak energy into air. And that's one way to design a leaky wave, I think. Okay, I can give you more to read about this if you want to read about this CRLH composite, right? Left-handed material. Okay. And of course, you can have other ways to design leaky wave antenna as long as you design something with a very small kx number. Like you can use periodic structures and use flocate mode excitation. Some of the flocate modes will be leaky, and then you use those flocate modes to work as a leaky wave antenna. Okay. So this, all I want to say about this and then the leaky wave, and let me go to the geometrical optics series. Okay. You put a dipole over here, you can actually extract ray physics out from this solution, and then thought that this was a different formula from what I usually write down. What I usually write down would be something like this: P12, R23, P21, e to the 2, I, K2, ZH, well, 1, 2I, K2, ZH, right? And the two formulas are the same. Let me just show you that they in fact are the same. Tij is 1 plus Rij. Hence I can write this as being equal to R12 plus 1 plus R12, R23, 1 plus R21 over 1 minus blah blah blah, okay, with the e to the 2 blah blah blah. But R21 and R12, how are they related to each other? Yes? Minus, right? So this can be compressed and written as 1 minus R12 squared. Right? So then I would have R12 plus 1 minus R12 squared, R23, e to the something, 1 minus R21, R23, e to the something, right? Then I can bring everything under the same denominator. And then this would be R12 minus R12, R21, R23, e to the something, plus 1 minus R12 square, R23, e to the something. Sorry, this will be R23. Okay? And then 1 minus R21, R23, e to the something. Can you see that this term and this term cancel each other? Okay? That term and that term. Can you see? They cancel each other, giving you this form. Okay? So, but this has more physical meaning, you're right. This has more physical meaning. Because I can now expand it as a geometrical ray series, or into a geometrical series can be resummed as a ray series. P1 to R2, 3, P2, 1, e to the 2i, K2, ZH. And then the next term will be something like T1 to R21 R23 squared T21 e to the 2 something. And then the next term will be T1 to R21 squared R23 cube e T21 e to the 2 something, right? And I guess I don't have to teach you how to do this expansion. I did it before. I did it many times before, I think. Seems like I've done it umpteen times before. So I don't need to do it, right? And you know how to do this. But each term has a physical meaning. The first term is just this reflection. The second term is just this ray. The third term is actually this ray. Okay, and then you can keep tracing. And you can apply method of stationary phase method, setter point method to evaluate every one of those terms. And then you get ray theory back. Remember when we apply method of stationary phase to a very complicated expression, we get ray theory back. If we apply the method of split descent and pick only the setter point, we get ray theory back. So you can extract ray theory back from this very complicated expressions, which I will not discuss in detail. I hope you know what I mean. And each term can be evaluated. And finally, this is the picture you get. Okay? You can read up about it in the textbook. Finally, this is the picture you get. Put a dipole source on top of a layered medium. The first term, you do the direct, maybe it's not good to put it there. Put the observation point here. The first term gives you the direct wave plus the reflected wave. This is the reflected wave. Okay. The second term, you will evaluate with a different phase, stationary phase point now, because that thing is important. When you find the stationary phase point, you have to incorporate that together with the e to the ik rho. To find the stationary phase point due to the second term, you put that in together with the e to the ik rho. In this picture, I assume that this term is unimportant. K1ZZ. Z is approximately equal to 0. Okay, so only these two terms control the stationary phase point. And then if you work that out, it corresponds to an angle that is like this. Theta 1. As if an image is being located here. Okay, that is the second point. And then if you go through the third point, again, this should be a 4. This should be a 4. Because you have to square the denominator, this should be a 6. So the second stationary phase point would be with a 4 here. And again, you will find out what the stationary phase point, it corresponds to the image location here. Okay. And it corresponds to a wave that has bounced like this. Okay? And you get ray optics back essentially every term when you evaluate with the stationary phase point method. This is minus 2d1. This is minus 2h1 minus 4h1 kind of thing. Okay, and then you keep going and you can get more and more images. So you have this geometrical optic series, which is essentially a ray optic series that emerges from this analysis. Okay? So the ray picture is good when the slat is thick. When the slat is thick, of course ray optics is always good when the frequency is high. Okay? So how high should the frequency be before ray optics is good? It should be that when the wavelength is much shorter than the wavelength of the slat, the thickness of the slat, then ray optics is good. Okay? So when lambda is much less than h, when the short wavelength limit or in high frequency limit, then ray optics is good. Okay? And then you can look at the physics through this ray optics picture. But when the slab is thin, what physical picture should I use? When the slab is thin, ray optics picture is probably not good, right? What picture should I use?
Do you mean same as lambda is approximate h?
Yeah, lambda is approximate h. What is the most expedient way to look at the physics of this interaction of the source with the slab? I use the mode picture, right? If the slab is not very thick, as I have shown you just now, I have K3 here, K1 here, K2 here. If the slab is not very thick, I only have 1 or 2 poles here. So if I were to use the model picture to look at the physics, it will be very efficient. Okay? So when the frequency is low, wavelength is long compared to the slab thickness, I use a mode picture. When the frequency is high, wavelength is short, I use the ray picture. Those two pictures are dual of each other. Okay? Like wave particle duality in quantum mechanics. So this is something like that. Okay? That when the wavelength is short, you look at the physics from one viewpoint. When the wavelength is long, you look at the physics from another viewpoint. Yes?
I'm so confused. You just now mentioned that the number of poles of the slab is small and lesser, right?
The number of poles, I also drew a picture where there were lots and lots of poles here. This is transformism. I draw a picture with lots and lots of poles here, right?
Right.
That corresponds to what? High frequency, right? And then if you were to look at this picture, you have many poles to get the physics correctly. That is not efficient. That is not good. So using the model picture when the frequency is high is not efficient. Of course, you can still do it with modern computers. You can use the model picture even when the frequency is high. But it's more efficient to use the ray picture. Okay? But when the frequency is low, use the model picture. You often come across this kind of duality in wave physics. Okay? A model picture, a ray picture. The ray picture is more like a particle picture. You treat the photon like a particle. Okay? And when you have a mode picture, you're treating the photon more like a wave. Okay, so it's like wave particle duality. And you actually come across this kind of physics quite a bit, even in quantum physics and also in electromagnetic physics. Okay, this wave particle duality picture. What is that? Does that answer your question? You have some question? You have some questions, maybe I never answer your questions properly.
No, I was still confused. Like, how did you get those higher number of poles? You said it was high frequency, but I don't know what that means.
When the frequency is high, do you agree that there should be many poles, many guided poles, guided modes in the slab?
Yeah.
Right? So if you search and look for the poles between K1 and K3, you'll see many poles there. Do you agree? That as the frequency gets higher, the number of poles that are guided by the slab is very large in number. So if you look at a model picture at high frequencies, you see many poles, which is an inefficient way to look at things. You get it now? Okay, good. Yeah, you remember you go study the dielectric slab problem in the undergraduate course. You have a graphical method and you find where it intersects. As the frequency gets high, you can find many intersection points. As you drop the frequencies, then it has only a few intersection points. Right? Something like that. Right? The graphical solution to the dielectric slab problem. Oh, the intersection points in your undergraduate course using a graphical method is the same as looking for poles. or looking for the solution to this equation. Okay, you can massage this into some transcendental equation involving circles and cotangents or something like that, and then solve this equation graphically. And if you remember that, the graphical method looks something like that, right? I don't remember my undergraduate course very well anymore. Maybe this is the slab thickness. You plot something like this. And then you plot circles like this, and then as you make the frequency higher, the radius of those circles gets bigger, and those intersection points are your guided modes. And the guided modes are solutions to this equation. Exactly the same. You don't believe me? You go home, look at this Fresnel reflection coefficient, and you can massage this equation into exactly what you find in your undergraduate course. Something like cosine, sine, cotangent, tangent. That very complicated transcendental formulas. They can be solved graphically. Okay. So is this clear? Okay. Then very good. We can move on then. Okay, just before we move on, I'd like to say one more thing, which is uniform asymptotic expansion. We have talked about simple asymptotic expansion. And we have used only very simple methods, because only simple methods can be taught in classrooms like this. Complicated ones are too difficult to teach, but you can read my textbook. There's a section on uniform asymptotic expansion. And when do you need to do that? You need to do that when simple method fails. Simple methods like stationary phase method fail, like the settler point method fails. And when does simple method fail? Simple methods fail when there is a singularity very close to the critical point. Like if we have a branch point over here, and then a settler point over here. If these two critical points get very close to each other, then the method of stationary phase would fail. The method of settler point would fail. Why is that so? Because the method of stationary phase point, for example, treats the integrand as slowly varying. Only the phase term is important. So you say only the phase term is rapidly varying, the rest is slowly varying. And hence I can extract the critical point using only the phase function. But that is not true anymore if there's a singularity nearby. What is the meaning of a singularity nearby? What is peculiar about singularity? A singularity is non-analytic. When a point is non-analytic, what does it mean?
Not single value?
Huh?
Not single value?
Not single value. There's one property of branch cuts and branch points, but it could be a pole. A pole is also non-analytic.
Non-differentiable.
Not differentiable, very good. Non-differentiable means that if you differentiate it at one point, the differentiation will go to infinity. Which means that the function is a rapidly varying function about that neighborhood. Okay? It doesn't matter, it could be this thing is kz is k1 squared minus k rho squared. This thing never seems to go to infinity. But if you differentiate it over and over again with respect to k rho, and then when you set k rho very close to k1, this thing will go to infinity. Its higher order derivative will go to infinity. That means that it's not smooth. These higher order derivatives do not exist. Okay, if it's not smooth, you cannot use the stationary phase point argument anymore. That the integrand is smooth, only the rapidly varying part is that part, and you cannot use the settler point argument anymore. You have to use this more complicated technique of uniform asymptotic expansion. And that is written up in my book. Okay, just be careful that next time when you go finding asymptotic expansions, when the singularity get close to each other, or singularity get close to the saddle point or the stationary phase point. Hope that some red flags will light up in your brain, say, no, I have to do something else. I have to do something else, and you have to read my book on how to do the correct one. Okay? So there's one thing I want you to okay. So another thing is that most of the time, the Sommerfeld integral is too hard to evaluate, and it's very hard to do all these asymptotic expansions. It gives you some physical insight for simple cases, but for some very complicated cases, like multi-layer medium and so on, you might not have the liberty and the luxury of doing all these simple techniques to elucidate the physics well. So you might have to do numerical integration. You will have to deliver some results for your boss. Your boss says, I want this Sommerfeld integral evaluated immediately. And then you scratch your hair and say, how can I do it so that I can deliver some results tomorrow? So you use a computer. You do numerical integration. Okay? So you have this Sommerfeld integral that you need to integrate. And it has this very complicated reflection coefficient. And it can be a generalized reflection coefficient so that this is very complicated. And you want to evaluate this numerically. What is the best way to evaluate this numerically? Well, this was an infinite integral because I want to do contour deformation. You would want to combine this into the Bessel function integral again, if you were to do numerical integration, because you save half the labor, right? Instead of going from minus infinity to infinity, you only integrate from 0 to infinity. Okay? And then you will integrate on the real axis, but you know that there are singularities that you will encounter. Like k1 is equal to 0, give you problems as you integrate on the real axis. So you would like to avoid integrating on the real axis. You will do something like the Sommerfeld integration part. By the time, Sommerfeld did not have a computer then, so he never thought about what to do when there is a numerical integration involved. But now, with the help of digital computer, you pick this path very close, or like the Sommerfeld integration path, and you pick a path like this, you are sure to avoid all the singularities you have in the integrand. You can prove that no singularities ever exist on this line. I think it's proved in my book. Okay, all the singularities will be above this line. And in the lossless case, the worst case is that you might have a singularity in region 1 and region n. So you might have a branch point singularity, which is a true singularity. And then another branch point singularity over there. Okay? And what happens to the other branch point singularities? What did you learn just a minute ago? The other branch point singularities are not there, right? So simple answer is not there. So you only have to worry about the first one and the last one. And then there will be pole singularities. Because they could be a guided sled problem that you're solving. Okay? And they might be pole singularities. Lots of them around. There might be leaky wave pole somewhere there. So you integrate along here and happily, you will not encounter any singularities. And of course, when rho gets large and z gets large, this thing will start to oscillate. But you want to deliver the result to your boss anyhow. You just make the integration step smaller and smaller. If rho and z gets larger, you just let the computer do the work. Instead of you using your brain to do the work. Okay? You just let the computer do the work and deliver an answer. Of course, when you do numerical integrations like that, you don't ask MATLAB to go from 0 to infinity. MATLAB will choke up and say, I can't return the result. You should divide this into sections. ask MATLAB to integrate each section by itself. Okay, MATLAB will not choke when you give a small range of integration. If the accuracy is not good enough, give MATLAB an even smaller range. And then you start collecting this into a bin. And then when the last bin contributes very little to the total sum, you start to ignore the last bin. And then throw out the last bin. And then if the accuracy is not good enough, you make this section smaller and smaller. And of course, you will use some quadrature rules like Gaussian quadrature, rhombus rule, Simpson's rule, Newton's cost rule. There are tons of rules that you can find in MATLAB. And you can find tons of rules in Abramovic's and Statham too to integrate. Okay, so that is the one way to do numerical integration. Okay? Yeah?
When your observation point is near, right, the things are not roughly varying. Does that mean the numerical integration works well for looking at the near field?
Numerical integrations work quite well in the near field because the integrand will not be rapidly oscillating. Not rapidly oscillating. And then integrations like this are quite easy to do in the near field.
But if you're in the near field, does that mean you need a lot of contribution on the table X?
That's a good point. That's a good point. There's a good point also because I never talked about the convergence of this integral. This integral is actually non-convergent. If z plus 2d1 equal to 0, then you're integrating something like this. Times an r tilde. Okay?